Three-phase transformer examples. In this presentation, we're going to be looking at determining which configuration would be correct for a three-phase installation that requires a transformer. And for some of the examples, we're also going to look at what's the required size of transformer that I can even get my hands on. And so this is a pretty common table that we will see given out by different manufacturers, indicating the common sizes that they provide. So I'll refer back to this every so often. It's certainly not something you have to memorize. It is merely a resource to give you a good idea as to what would be done in the field. Well, let's get going then. And we're going to start with this. This is a 208 volt, three-phase, 30 amp load with a power factor of 1. And it's going to be connected to a 600 volt three-phase supply. And what we're going to purchase is a manufactured three-phase transformer. And what that means is that we don't need to build the bank of single-phase transformers. Now, the first thing we want to do is determine what is the configuration requirement. Well, we've just got a straight voltage given here and a straight voltage given here. And what straight is in reference to is that there's only one voltage given. Whenever one voltage is given, it is always assumed that it is the line voltage value. And since there's only one voltage, we can safely assume that there is no need for phase values. Due to this, the most logical type of configuration will be a delta-delta. The delta will have a 600 volt rating on the primary because that is the supply end, and it will have a 208 volt rating on the load side. So the H terminals will be on the primary and the X terminals will be on the secondary, as this is a step down transformer. Now, what size of transformer do we require? Well, to do the calculation, we need to know the total kVA. The total kVA we can then determine quite easily by taking E line times I line times √3. And because we have I line on the secondary, we know it's a 30 amp load, we'll use that value. 208 volt times 30 times √3 gives me a total of 10,807 VA. Transformers are always rated in kVA if they are over 1,000. And due to that, we would need a 10.8 kVA minimum transformer. Now let's take a look at our three-phase transformer sheet here. It looks like they don't make a 10.8, which is going to be a weird number. But if we take a look at the kVA column right here, these are three-phase transformers, and it looks like a 15 kVA is what we would then purchase and install. So we'd have a little extra capacity there. Let's take a look at another example. This time, we're going to use a transformer bank that is going to be single phase. And this single phase transformer bank is going to have a 480 volt three-phase load that is 100 amps. And the source is high voltage 4160 volt three-phase. Now at this point, because they are straight voltages, it really is up to us yet again to determine, are we going to do it in delta or Y? Now, most often, it is the selection to go with delta because the amount of current that each individual single-phase transformer would need to be able to carry will be less if connected in delta than if we were to choose Y. So for that reason alone, what we're going to do is install or select at least 3 4160 to 480 volt single phase transformers. Now these transformers will have 3 of them, and due to that, we're going to connect them in a delta form. 4160 volt three phase coming in on the primary, so that's my H terminals, and 480 volt three phase on the secondary, that would be my X terminals. Now we know what type or voltage ratings we need for our transformers. What about the kVA size? The total kVA for this entire installation, we can again use the same formula, E line I line times √3. If we are then to apply the 480 volt times 100 amps on the secondary by √3, we end up with a total VA requirement of just over 83,000 VA. Now that would then mean that we have 83.13 kVA total. But we're not purchasing a three-phase transformer. Rather, we are going to purchase three individual single-phase transformers. And due to that, we can take the total value and divide it by 3, giving us a 27.71 kVA minimum requirement for our individual transformers. So let's just go back to the original data sheet here and see what they have to offer. We're looking for 27.71. And if we take a look down here, it looks like the closest we're going to get is 37.5 kVA. And that's about as close as we're going to be able to get because 25 will be too small. So a little bit extra capacity there as well. And what you get the idea of is that when we size a load to a transformer, it is most likely going to have a little extra capacity because it's very rare that we are going to end up hitting it right on the money. All right, well, let's take a look at another example. This one, what we're going to look at is, again, a single-phase transformer bank. And now we've got a slash voltage on the secondary. The slash says 347/600 volt, three-phase load, 200 amps. When I see this, my initial thoughts, this is the rating that we would see on a standard 200 amp panel board that serves both three-phase loads and single-phase 347 volt loads. So this would be a 4-wire load. And the assumption we can draw that from is because it has a slash and says 347/600. Now the primary is 40 volt 3-phase source. Now, due to the most common orientation that we're going to see in industry, we are going to be building the single-phase transformer bank with the primary in delta. The secondary, because we need phase voltages and line voltage, we are going to construct it in Y. So let's take a look at what we have. So at this point, we end up with 3 individual transformers, each one having a voltage on the primary of 480 volts. But watch the secondary, each one being in the phase orientation, and because it being Y, if we want 600 volts and 347, it means that each one of our secondaries for our transformers need to be rated 347 volts. So we have 480 to 347 volt single phase transformers. What is the total VA requirement? Well, same process yet again. And what we see is that we have E line times I line times root 3, which gives us 600 times 200 times root 3, and a total VA of 207,000. Of course, when this is further reduced, we get 207.8 kVA. And remember, we're selecting individual single-phase transformers, so that means we need to take this value and divide it by 3. When we divide it by 3, we get 69.2 kVA for each individual transformer. And so when we go to select our transformers, we look in our table here and we look at the manufacturer and they say, well, we make a 50 and a 75. So you decide which one you want. And so if we want to ensure we have enough capacity, we would need to go with the, well, kind of hard to see there, 75 kVA individual transformers. All right, well, let's take a look at a different view on this. And that would be, what if we start with 3 single-phase transformers that are rated 120, 240, 5 kVA, and then we look at all of the basic configurations that we could possibly do, and that would be Y, Y, delta, delta, Y, delta, delta, Y, and finally open delta. Well, for each one, we're going to have a different source voltage and a different load voltage that it could accommodate. And so this is an important consideration to make here. Just because it says 120 volt and 240 doesn't mean that we can connect it to any type of 3-phase source that has those numbers in them. So let's first start with a Y to Y 3-phase transformer bank. So Y to Y, what we would then have, 120 volt in the phase, 240 volt in the phase. And what we can see is that I've run a neutral here, and the neutral would have 240 volts from line conductor to the neutral, 240 being a pretty common three-phase voltage down in the States and definitely in Europe, 416 being the line value. Now, the total for this would be 15 kVA. That's the total capacity that this transformer bank would be able to supply. Now, why have I not put a neutral connection on the primary? Well, typically, and this isn't a rule, but 99.9% of the time on the primary, if we're doing step down, as in this is the supply side, we don't connect to neutral because the neutral is not required for any sort of unbalanced currents. I know it's a little bit odd, but we're only ever going to really see a neutral on the secondary if indeed we have a bizarre scenario like this, where they are both Y on the primary and Y on the secondary. Let's take a look at another example with this. We're going to do delta delta now. Same transformers, and now we see that the three-phase incoming source voltage would be 120 volt line value. Now, this would be a very odd arrangement indeed, because 120 volt three-phase doesn't really exist in our common world here. There are some situations where you can see that value of voltage for motors, but this is really uncommon. Over here, this is a very common three-phase voltage value of 240. Again, total kVA is 15 kVA because we have three transformers. Well, let's take a look at a blend of the two then. We're going to do a Y on the primary and delta on the secondary. Same transformers yet again. We have 120 to 240. This time on the Y side, I have a 208 volt source three-phase voltage, which is very common, and a 240 volt three-phase voltage on the secondary because I've connected them in delta. Again, total kVA is 15. Well, what if we were to flip this then and instead do delta on the primary and Y on the secondary? In this situation, we again have that odd three-phase voltage that would be exceedingly uncommon. But over here, a very common American and European three-phase voltage, and at times this may be necessary if we have equipment that's come from overseas. We have a motor that's rated for 416 three-phase from Europe, and it's not simply something we can replace with a comparable North American unit. In that situation, it might be advisable to put a transformer in order to get this voltage. Now, of course, this over here, probably not something we're going to be dealing with, as 120 volt three-phase sources are not really a common occurrence. Finally, we can do the energy efficient or space saving or cost saving measure, which is an open delta. Now we're still using 120, 240 volt three single phase transformers, but only two of them. And because of that, we then have a reduced capacity. Notice that the three-phase incoming voltage is the same as the delta on the primary of one of our previous examples. And the 240 volt line value is the same as the delta connection on one of the other previous examples. The main difference in the delta, full delta to open delta, is the total kVA. I've done two calculations with the two percentages. 15 kVA would be the comparable full delta, would have a 57.7% reduction. And the 10 kVA, well, not reduction, but it would be 57.7% of the total 15. And the 10 kVA, which is what is currently connected, we could do a calculation with that, and it would be 86.6% of the 10 kVA. Now note here that it's a slight difference between the numbers, but for any sort of examination or assessment, this would never be two possible corrective values that you would have to choose from. And in reality, the difference between those two is almost non-existent.